In this video, we're going to see some ways to solve trigonometric equations with identities and verifying some of these. So I'm going to go through some of the identities, not really go into depth into the why and how of them. It's more like here they are, let's use them. So first, trig identities, you should have saw in the last video that there is one Pythagorean identity that we saw, which is this one, and then I mentioned that there are two other variations that also have their alternate forms. I'm not going to go into showing the alternate forms because the steps should be very similar. And what I'm actually going to do is we're going to derive these ones from this original one. I'm going to call this the OG. And to do that, we're going to start off with the regular function, sine squared theta plus cosine squared theta equals 1. And to do that, to get to one of these, we're just going to divide. Let's divide by, let's do alphabetically. Let's start with C. So we're going to divide the left side by cosine squared theta. And if you do it to the left, you have to do it to every term. And whatever you do to the left side, you have to do to the right side. So now we have sine squared over cosine squared, or sine over cosine, that if we remember, tan is tangent. Tangent is equal to sine over cos. So we're going to rewrite this. This turns into tangent squared theta plus this turns into a 1 equals 1 over cosine, and we'll see this later. 1 over cosine is actually its counterpart, secant. And this is going to be secant squared in that case. And we actually verified the third identity, so scratch this out. This is the third identity. And here we have it. Tangent squared, again, it's rewritten differently. And now we're going to derive the second identity. And here we divided by cosine, so we're going to do it the other way. So sine squared theta plus cosine squared theta is equal to 1. We're going to divide everything by sine squared this time. And sine squared over sine squared, that turns into 1, plus cosine squared over sine, we're going to see that later. It's actually cotangent. Cotangent is equal to cosine over sine. So cosine squared over sine squared, that's going to give us cotangent squared theta. And 1 over sine squared, that's actually the cosecant. And we'll see that later. So here we have cosecant squared theta. And we have just proved or verified the second identity. Now again, these three are very important because you have to know their two other different variations. So I'm not going to go into them, but please derive them yourself and get familiar with them. So here, I'm just going to talk about the identities. So here's one pair of identities, which is the even and odd identities. Notice what this is saying. This is saying the tangent of the negative angle. So for example, tangent of negative 45, that should equal 1, negative 1. That's the same as the negative of tangent of the positive 45. So currently, off the top of my head, I don't know what tangent of negative 45 is, but using this property, I know that tangent of positive 45, I know that one, that's 1. And that means, according to this property, that tangent of negative 45 is equal to negative 1. And we can use similar reasoning for sine. Sine, notice, is an odd function, so these are odd. These are odd. These are odd. And these are even. Notice, if you recall from your even and odd work, even and odd, odd said f of negative x will give you negative f of x if it was odd. And if it was even, you would get f of negative x will give you the same positive f of x. So be aware of that. We're going to be using that in a few problems coming up. So we have the reciprocal identities. I like to call them their counterparts, as you've heard in my videos. Sine, its reciprocal identity is 1 over cosecant. Cosine is equal to 1 over secant. This is something that students always confused, since sine starts with an S, people think it's 1 over secant. Similarly for cosine and cosecant, but that's the opposite, right? Since it starts with an S, this one's going to be a C. Since this one starts with a C, this one's going to be a S. And then we know tangent and cotangent are counterparts. So these are the other way around. Quotient identities, this is basically when you break down tangent into sine and cosine. So I would write that on the side. For a reminder, what is the quotient identity? It's basically changing it to sine and cosine. If we continue on, we have this summary. It's basically the last ones that I gave you, and the reciprocal identities, basically all of them together. So what we're going to do is we're going to use these in the next examples. So let's see them in action. We're actually going to skip this first example because we're not going to use a graphing tool. We're going to jump into this one. We're going to verify that this is true. Tangent of theta times cosine of theta is equal to sine of theta. When you're working with any verifying or proofs, I say my recommendation is change everything to sine and cosine. Oops, sine and cosine. And this is the long way of sine and cosine with the e at the end. So let's take that advice. We're going to apply the tangent theta. To change it to sine and cosine, that's actually going to be my quotient identity right here. So sine of theta over cosine of theta. And I'm highlighting the identity because there's homework problems for certain students at certain schools. That's part of their process. You have to say which identity did you use. Well, I used the quotient identity. So I'll bring this down, bring down the cosine of theta. And is this true? Does it equal? I like to put a question mark. Is this true? Well, cosine and cosine cancel. It turns into 1 sine of theta times 1 sine of theta equals sine of theta. Nice, I proved it. In some proofs, you'll see a little box filled in. That means I've proved it. I'll skip this. Jump to here. Verifying the equivalency using even odd identity. So here they gave you kind of like what to use. Even in odd identities, I can see here my even and odd identities involved a negative value. And if we remember sine said sine of the negative angle is equal to negative of the positive sign. So let's do that here. We're going to do 1 plus sine of x. 1 sine, again, it told me sine of negative x, that's the same as negative sine of x. So I'm going to substitute that here, sine of x. And we're trying to prove, is this equal to cosine squared of x? Well, I can FOIL this out, but I'm going to use something that's going to come up later. This is called my difference of squares. And it is a powerful shortcut of squares. And it says you can factor this into a plus b and a minus b. Sorry, and backwards. So if you have it factored, you could turn it into a squared minus b squared. So if you notice, here's my a, here's my b. So according to that formula, 1 squared minus sine squared x, is this equal to cosine squared x? Well, it's hard to see maybe, but this is one of the alternative forms of our Pythagorean theorem. So here, I can solve it real quick. If I subtract sine squared on both sides, subtract sine squared, subtract sine squared, these will cancel, and you'll see right here that's equal to cosine squared theta. So this turns into cosine squared theta, or x in our case, and these are true. So we've proved it. Cool. Remember this one. This is very helpful. Verifying a trigonometric identity involving secant squared. So the fact that it has secant squared, I automatically think about, oh, I've seen that in one of my trig identities. So let's see if I can use that. Secant squared theta minus 1 over secant squared theta. Is this equal to sine squared theta? Let me look at my trig identity for it. So I have 1 plus tangent squared equals secant squared. So 1 plus tangent squared is equal to secant squared. Notice I'm omitting the angle just only because I want to go a little bit faster. So it kind of looks like this one, but I need to manipulate it. So what I'm going to do, I'm going to subtract 1. Then I have tangent squared theta, in this case, is equal to secant squared theta minus 1. Well, I could substitute that for tangent squared, but I'm not sure where this will go. But that's part of the beauty of math. So let's try it. So this is the same as tangent squared theta, so I'm going to substitute that. Tangent squared theta over secant squared theta. Does this equal to sine squared theta? Well, remember my suggestion up here, change everything to sine and cosine. So let me do that doing some quotient identities, right? So quotient identity says tangent squared is sine squared theta over cosine squared theta, and secant squared, its reciprocal identity, is 1 over cosine squared theta. Does this equal sine squared theta? We're almost there. Well, dividing fractions, we have to keep change flip. We keep the first fraction as it is. We multiply and we flip the second fraction. And we're just going to keep going. We're going to cross cancel cosine squared and cosine squared. Sine squared times 1 turns into sine squared theta. Does that equal sine squared theta? Yes, it does. So we are done. Nice. Cool. Let's keep moving. Creating and verifying an identity. So we're going to create an identity for the expression by rewriting strictly in terms of sine. So we're just going to simplify this basically. And we want to turn everything, we want to have it all end in the terms of sine. So it just should have sine. So let's change things to sine and cosine. So tangent, according to the quotient identity, is sine theta over cosine theta. Secant theta is, with the reciprocal identity, 1 over cosine theta. And we're going to multiply straight across. 2 times sine theta over cosine times cosine is cosine squared theta. They want everything in terms of sine, so I need to change this cosine squared. And actually, we derived it, I think, in the past one. Where is it at? We derived it here. Cosine squared is 1 minus sine squared. So what we're going to do is we're going to rewrite this as 2 sine theta over 1 minus sine squared theta. And we have rewritten it in terms of sine, with some constants, but that's completely fine. All right, we're going to continue with our work in even and odd identities. So we're going to bring them back. So remember, cosine and secant were the only functions that are even. All other ones are odd. So with that information, we can change the sine squared, negative theta, to, actually let's work with the denominator first. Minus cosine squared, negative theta, over sine. Negative theta, sine of negative theta, remember that is negative sine of theta, again for my identities. Cosine is the even one, and that one said that's the same as positive cosine of theta. So I'm just going to rewrite that here, cosine of theta. Does this equal cosine theta minus sine theta? Well, in the numerator, what I'm going to do is I'm going to use my properties again. Sine of negative theta is equal to negative sine of theta. So what we're going to do is substitute. I'm going to substitute. I know it looks like equals here, so it should be a negative right there. So negative sine of theta squared minus cosine of negative theta, that's the same as cosine theta squared. And do these equal. In the denominator, I'm going to do something interesting, which you should become familiar with. They both have a negative here and here, so I'm going to factor out a -1. So -1. And then I just divide negative sine theta by -1 is positive sine theta. Negative cosine of theta divided by -1 is positive cosine theta. And in the numerator, I can simplify some more. Negative sine squared is just sine squared minus cosine squared theta over negative sine theta plus cosine theta. Now moving down a little bit down here, sine squared minus cosine squared, I showed this property earlier. This is actually a difference of squares. And if you remember that formula, it said I can rewrite this as sine theta, plus cosine theta times sine theta minus cosine theta. The denominator is still negative sine theta plus cosine theta. Now you should see I can cancel these out, and I have sine theta minus cosine theta over -1. And we're trying to get to this. We're almost there. The beauty of math is this negative, instead of putting it at the denominator, I can actually distribute it in the numerator. So now this is the same as negative parentheses, sine theta minus cosine theta. And once I distribute it, so I'm sorry I'm going down over here, it gives me negative sine theta plus cosine theta. And I know it does not look exactly the same, but now I have proven that these two are equal. Again, the cosine is positive in both, and the sine is negative in both. All right, let's keep going. Verifying identities involving cosines and cotangents. So for this one, good question. So we could use some identities, our Pythagorean identities, and they are here. 1 plus cotangent, that's cosecant squared. So 1 plus cotangent, this should be the same as cosecant squared, and this should be the same as sine squared. And let's just jump into that. So let's change it. 1 minus cosine squared is sine squared x. 1 plus cotangent squared is cosecant squared x. Does this equal 1? Well, let's change this using our reciprocal identity. So this is 1 over sine squared x. And we see now that these cancel, and it does give us 1. All right, writing the trigonometric expression as an algebraic expression. So this is handy, especially in calc. When you do integrals, we want to be able to change this into an algebraic expression. So it may not be visible to the eye, but a very common step that we notice here is This is some number squared plus another number minus 1. This is very common with quadratics. And if we replace, so let's let x equal cosine theta, then since this is 2 times cosine theta squared, and the other one is plus cosine, then we subtract 1, and we have 2x squared plus x minus 1. And now we have expressed it as an algebraic expression. Next one, we want to rewrite a trigonometric expression using the difference of squares. Now this one, we've seen it a bit already. That's that a squared minus b squared will give us a plus b and a minus b. If you can't see it easily, it's always good to notice your perfect squares. Well, 4 is a perfect square, 1 is a perfect square, cosine squared is a perfect square. So what I could do to get a and b is I could kind of like square root these individually. In my mind, you can't do that in real life, but in your mind, you can square root them. Well, 4 cosine squared theta minus 1 will turn into square root of 4 is 2, square root of cosine is squared is cosine. And then the first one is plus square root of 1 is 1. And then times 2 cosine theta minus 1. These are conjugates. Again, another math term, hopefully you remember it, conjugates. And there you have it. There's an expression written as a difference of squares. Now for our last one, we're going to simplify by rewriting and using substitution. So we're going to rewrite this cosecant squared minus cotangent squared. Cosecant squared is at one of our Pythagorean identities. Cosecant squared minus cotangent squared. And actually, that's one of our easier ones. What we're going to do is if we have 1 plus cotangent squared theta, and that equals cosecant squared theta. Let me see if I got that right. Cotangent squared is right there. And then we see that it's 1 plus cotangent equals cosecant. So let's double check. All right, so here's what we're going to do. We're trying to get to this. And notice we do have cotangent squared and we have cosecant squared already. Cosecant is positive, so that one's good. Cotangent is positive, but on the other side. So what we're going to do is let's subtract cotangent squared on both sides. So now I have 1 equals cosecant squared theta minus cotangent squared theta. And you have just simplified it to equal 1. And that's pretty much it. But the main idea for this section is knowing how to use your identities in different forms. So pay attention, go to SI, and do some more of these. So I apologize for the dog in the background.